Hi, my name is Corey Carpenter, and today we're going to be looking at a supersonic triangle going at Mach 3 at about a 45-degree angle and see what kind of shockwave it creates in high-speed aerodynamics 1. All right, so first we're going to go look at our geometries. We're going to focus on drawing a perfect triangle. We're going to start with half of it. All right, so we got it nice and loaded. We got here, you're going to start off by drawing half a triangle. In our case, our back of our triangle is going to be about 30 centimeters. So we're going to half it and do it by 15 centimeters. And we want an angle of 45 degrees. So you want that right here. And then it'll automatically calculate the length of that needed to get a 45-degree angle, but with that length of 15 centimeters. I'd also recommend creating a smaller triangle here to do finer meshing. This will help make it a little bit more accurate, and we're going to refine that in the meshing process. And this is going to be our far field, and it's going to be a little bit less meshed, but still pretty finely meshed to like about e to the -2 power. So next, let's go on to meshing. Definitely only do half of the triangle. It makes it way easier and way quicker, and you can do computation a little bit faster. All right, so we're going to switch over to our meshing. Let's see. All right, so this is our meshing. We're going to want to start off by going to mesh, and we're going to change our variable right here for element size to the -0.1. You just put a 0 there and 0.1, and then that'll make it way more refined. And then you're going to select this area right here. After that, you're going to go and click mesh, insert. You're going to want an inflation and sizing. I'd go with sizing first and select your inner triangle and refine that to e to the -3rd power, which is about 0.001 in that location right there for element size. And after that, you're going to introduce your inflection. You're going to select your geometry, which is going to be this triangle right here. And you're going to want to select the boundary conditions for your inflection. You want your inflection to be based around this the triangle right here. That way it ripples out from it and it makes it way smoother and way more accurate as you get close to the triangle. And for layers, I went with 6. You can go with more, but it's just the amount of concentrated ripples towards it. Accept that, and then you hit generate mesh, and then you should get something about like this. As you can see, it's pretty fine, but once you get the triangle, it looks solid black because of how fine it really is, especially as you go along. It kind of like does some 3-dimensional, 4th-dimensional trickery here. And yeah, see, it's very fine there, so it'll be very accurate once you get to the triangle. Now, before we start doing any testing, we're going to want to create some named sections. First, start with the bottom layer. You're going to want to name it symmetry. So using your control mouse or control button, hit control, and then select every line that is on the bottom. And then you're going to right click, put create name section, and you're going to want to name it symmetry because this will create a mirror effect when you do the calculations. And next, you're going to want to create your far field condition. This will just be a calculation where it's taking a Mach 3 airspeed throughout the whole testing chamber, which is about this entire rectangle. You can make it a little bit bigger. It'll probably make it a little bit more accurate, but this is what I went with. So you're going to select it just like the other one. Bam, bam, bam. Right click and click to create name section. Call it far field. It's going to show up as a wall. Don't leave it as a wall. I'll show you how to switch in a minute once you get to the testing section. And last, you do want to create a wall, which is your triangle right here, which you're testing. So you're going to do the same thing and name it wall. And now we're going to go over to the testing software and see what you do to set that up. Let's see, we're going to go to Fluent. Sure you guys are seeing that. All right, sweet. All right, so you're going to get this mesh right here, and it should import. If you're not seeing the full image, you go to View, Views, and then hit Symmetry and Apply, and it should reflect the image, and you'll be able to see the entire thing and the contours reflected along the Z axis, I believe. And before we get to iterations, all that, let's go to General. Make sure it's density based because our density is going to be changing with the pressure of the ideal gas, which is going to be air. And then for models, make sure you're using K omega and energy is on so we can get temperatures. All right, let's go to materials, go to fluid, air. All right, we're going to want our air to be an ideal gas. It's going to stay it's going to show up as constant at first. Switch to ideal gas. Make sure it's changing, because if it's not changing, you're going to be out of luck with anything. It won't move. The air will just do nothing. You won't get any shock waves whatsoever. Next, boundary conditions. This is what I was talking about before. Your far field is going to show up on here, right here, as a wall. Switch it to pressure far field, and this dialog box is going to show up, and it's going to be about 0.6 Mach number. Switch it to 3 to get about the same simulation as this. If you want to do it more and go crazy, go ahead. And your thermal is going to be about 300 Kelvin. You can leave that. There's nothing, no constraints related to that currently. Hit apply. Double check that your wall is labeled a wall. It should be, but just in case. And same with your symmetry. Make sure it is labeled as symmetry. In here, you see it automatically does it. So you got a little G code there. All right. So right before we load everything, we're going to want to go into report definitions. I have already created 2 report definitions for this case, for the drag coefficient and the lift coefficient, but I'm going to walk you through how to create your own. You're going to click this, and you're going to click new, force report, and let's say we want to know the drag coefficient. Go in here, and it's going to take the forces along the x1 into the 0 direction of y. And you're going to want the drag coefficient, and it'll generate a report. Hit compute. Oh, what happened? We didn't select wall. So you got to select wall first, and that's your conditions where it's testing your coefficient of drag off. Hit that. And then you got a coefficient of drag of this value right here. And let's say you want coefficient of lift. I'll show you that real quick. We got negative 2400.9 because we had a negative force pushing it down, so it's going to make it negative. All right, so all that is set up. We're going to go to initialization. You're going to initialize and then run the calculation. You can run it as many iterations as you want. I usually had to converge around like 1,200 to 500. So I do like 1,015 or 1,500. That should be pretty good. Select solution steering and select Supersonic, and that's going to help you steer towards the supersonic convergence. Hit calculate and wait for it to run. Once you get your results, just go to graphics, contours, and we can create a new contour for whatever we want. Let's say we want a pressure, static pressure. Save and display it. And here's our static pressure. All right, so we got it in pascals. As you can see, there's a huge pressure in the very front of it. That's due to the stagnation of velocity towards the front there. So it's going to be a higher pressure. And that higher pressure is going to create this huge wake right here. You see with this bow. And that's going to probably induce a little bit more drag than we would want. And you can see the borderline right there. And I can show you how to do a couple of the others. Let's say you want a Mach number. Go to velocity. Select Mach number. Bam, here's your Mach number. All right, you want regular velocity? Here you go. Not X direction. Here's your velocity magnitude. Here's this. Pretty much the same shape. As you can see, the velocity is lower where the pressure is higher, and the velocity is higher where the pressure is lower. They should work in vice versa of each other. Temperature, you're going to see more temperature behind it due to the negative pressure or the high pressure wake behind it, which is very interesting. And then let's say we want density right here. There's a higher density in the front because of all the air being shoved into that triangle. And I think that's about it. Pressure, density, velocity. All right, that's about it. And then we got our coefficients. We got that. Let's say you want some streamlines. Let's switch to the post-operational processes, and let's go see if they can show us some nice proper streamlines. It's going to take a second while it loads. I forgot to load this up prior. All right, so this is our final little post-op. This is going to be our streamline. If you want to see this like myself, you're going to hit this streamline button, create a new streamline. You're going to select about 500 points, and you're going to start from symmetry 1, and that way you'll get everything included. And for velocity, click apply, and then you're going to get about the same streamline right here. And then this shows you the velocity as it hits the wake. The particles hit it around here, and as you see, it curves around it in this way here. And there's a flow reversal right here at the very back in this cool formation right here that looks like a spade. And that's about it. Thank you so much, everyone, for watching. I hope you have a splendid day.